Okay, so thank you for the introduction and for the invitation. Of course, it's a very good opportunity to speak to you. Good morning, at least to those in Europe, afternoon in Asia, and for those of us west of the Atlantic, well, it's time to go to bed. I'm Dinis Abranches, and I'll be talking a little bit on how to model DESs with sigma profiles. Now, because we cannot model what we do not understand, I'm going to start by discussing what DESs are. And this is a common figure when discussing DESs, and it shows a eutectic-type solid-liquid phase diagram with a eutectic point and a straight line connecting the melting points of the pure components. Now, there's two things that we need to acknowledge. The first one is that having a eutectic-type phase behavior is not a trait of DESs. Most mixtures of organic compounds display this behavior. Second one is this straight line that connects the melting points has no physical meaning, and it's not what we should be comparing against when discussing melting temperature depressions. Finally, this eutectic-type behavior does not arise from intermolecular interactions in the liquid phase. And to try to convince you of this, allow me to show you the phase diagram of benzene and cyclohexanol. We have a beautifully shaped V-shaped phase diagram. We have a melting temperature depression of almost 60 degrees, and yet there's not a single hydrogen bond across these two components. And if you're not convinced, let me show you 2-pentanol with cyclohexane. Cyclohexane is fully apolar. And again, a eutectic-type phase diagram, a melting temperature depression of almost 100 degrees. And again, not a single hydrogen bond is being formed between these two precursors. In fact, not even dipole interactions are being established. And yet, we still have eutectic-type behavior. So what are DESs? Start by solid-liquid equilibrium. This is the equation that governs eutectic-type behavior, those phase diagrams that I just showed you. And it has two main contributors to it. The first one are the melting properties of the pure components, enthalpy of fusion and melting temperature. And the second one are the activity coefficients. The activity coefficients, it's what tells us, what describes the interactions in the liquid phase. Now, let's bring up an abstract mixture of components A and B. Again, the straight line that connects their melting points has no physical meaning. And now let's look at the ideal case. So let's say that the interactions in the liquid phase between A and B are of the same strength as the interactions between molecules of A and molecules of B. In this case, the activity coefficient is 1. And, well, the gamma drops out of the equation. Nevertheless, we get eutectic-type phase diagram with considerable melting temperature depressions that arises only from a statistical phenomenon due to the pure component properties and not due to interactions. This is not a DES. This is simply a eutectic mixture. If you use it as a solvent, it is a eutectic solvent. It's not deep. The deep part of eutectic solvents arises from strong interactions between A and B. In these cases, we have gammas that are below 1, we have deviations from ideality, and we have a diagram that looks like this. The melting temperature depression is larger for the red case, but it's composed of two contributions. If we take, for instance, an example of mole fraction of 0.5, first contribution is the melting temperature, ideal melting temperature depression, which comes only from the melting properties of the pure components. And then this red region here is a melting temperature depression due to strong interactions in the liquid phase. This is what defines a DES. Now, how can we design DESs? Well, we want to use precursors that establish strong interactions between themselves, but those interactions have to be stronger than the interactions between the pure precursors. And the way to achieve this is to use lone hydrogen bond acceptors or asymmetric hydrogen bond donors. Let me give you an example. Asymmetric HBDs. Very nice case of this is thymol. So thymol has an OH group directly bonded to an aromatic system. So we have resonance effects here. The benzene ring acts as an electron withdrawing group, and the OH becomes more positive than usual, which means that the HBD becomes more positive, therefore a better HBD, but the oxygen, the HBA, also becomes more positive, therefore a worse HBA. And this is a nice place to introduce sigma surfaces and sigma profiles. We can take this molecule, optimize it in DFT with a COSMO continuum solvent model, and we can look at its sigma surface. So basically its polarity inscribed on its surface area. And you can see that the positive part of this molecule, the HBD part, is much more pronounced than its negative polarity part. And we can take this and build a histogram, the sigma profile, where the y-axis is simply the surface area of the molecule that has a given sigma value. We have three regions here: the HBD region, the apolar region, and the HBA region. And just by looking at it, we can see the asymmetry in thymol. We have a much more pronounced peak in the HBD region than in the HBA, which means that we can mix thymol with a plethora of different compounds and obtain DESs. For instance, this is thymol and methyl. Notice the similarity between the two molecules. The dashed line is the ideal phase diagram, and we get severe melting temperature depressions because we have very, very strong negative deviations from ideality. Another case are lone HBAs, and very good example is betaine. It's a natural compound. It will surely interest you for natural DESs. Betaine is a Zwitter ion. We have a formal negative charge and a positive negative charge. However, the positive charge is shielded by methyl groups. So when we look at the sigma surface, we see that we have a very pronounced negative region, but almost no positive polarity. The sigma profile tells the same story. We have a very strong peak in the HBA region, but almost no HBD capability, which means that we can mix betaine with different HBDs, for instance, thymol or salicylic acid, and get strong deviations from thermodynamic ideality, here depicted as dashed lines, and thus severe melting temperature depressions. You can even mix betaine with compounds that are not good HBDs. Well, you can mix it with methyl, which is good HBD, but also coumarin and camphor, and still get negative deviations from ideality. In fact, in this work, we measured the phase diagrams of several betaine-based mixtures, and we plotted the melting temperature depression at a random mole ratio, in this case, a 1-to-1 mole ratio, and we found a very good correlation between the melting temperature and the excess positive polarity of the second compound, which we defined as simply this integral minus this integral. And not surprisingly, thymol was the second compound that led to the largest melting temperature depression. But what's interesting is sorbitol was one of the worst performing cases. And if you look at sorbitol, you have a larger positive polarity area than thymol. The thing is, sorbitol, which is a collection of OH groups, also has a very strong HBA peak, which means that sorbitol interacts very well with itself. And so thymol outperforms it by almost 100 degrees, which gives us the impression that when designing DESs, we can use compounds that are good HBDs that establish a lot of hydrogen bonds with the second compound. But what matters for negative deviations, it's the asymmetry in their polarity, not their ability to hydrogen bond. And this also impacts how water affects these diagrams. I'm just going to fly by these, but betaine, we studied the impact of water on betaine urea and choline chloride urea, and the impact of water on the first case is much more severe than on the second case. And if we look at the activity coefficients, we find that water enhances the interactions between betaine urea, while for choline chloride and urea, it's the other case. We even get positive deviations from ideality when we start adding water to the system. Now, sigma profiles, we can use them as a qualitative framework to give us some intuition on which precursors to choose when designing DESs. But we also have a quantitative framework that allows us to predict the phase diagram of these mixtures. COSMO RS sigma profiles were developed as inputs to COSMO RS. So say you're interested on the solid liquid phase diagram of a binary mixture. You can generate your sigma surfaces using DFT, and from them you can get sigma profiles, and you can use the sigma profiles as input to COSMO RS. You then ask COSMO RS to provide you to estimate the activity coefficients of the mixture at a given composition and temperature, and you feed this information into the solid liquid equilibrium equation. And then you solve this in an iterative fashion. So let me give you, we've done a lot of works using COSMO RS to predict the phase diagrams of DESs. I'm just going to give you a couple of examples. First one is regarding terpene eutectic mixtures, also natural compounds. And the red dashed lines are the ideal predictions, while the black full lines are the predictions by COSMO RS. And these predictions are done without any experimental information about the mixture. And yet the predictions are very, very good. This is methyl thymol, thymol camphor, and even in the ideal cases like methyl borneol or methyl sorbitol, COSMO RS performs very, very well, which means that you can calculate the sigma surface of hundreds of precursors and very quickly identify which ones will have severe melting temperature depressions. This is another example more recently where we liquefied flavonoids with terpenoids. And again, dashed lines are the ideal predictions, full lines are the COSMO RS predictions, and we have very, very accurate results. Now, these two cases were type 5 DESs, which are composed only of non-ionic species. The story changes for type 3 DESs because COSMO RS is not very good at predicting activity coefficients of salts. And to give you an example, in this work, we studied its ability to predict the phase diagram of choline chloride-based eutectic mixtures. And we tried two approaches. The first one was optimizing the sigma surface of choline and of chloride separately. And the second approach was to optimize a electron-neutral pair. So we choose a particular interaction conformation and we optimize that as a single neutral molecule. And although the first approach is more faithful to reality, we found that the second approach provided much more accurate results, particularly this conformer here. And the reason for that is that when we're using COSMO RS with strongly densely charged ions, it tends to underestimate their negative deviations from ideality, which underestimates their eutectic temperature. Nevertheless, using the AB approach, particularly this conformer, I'm showing you here the predicted eutectic temperature against the experimental eutectic temperature. And sure, we have some exceptions, but overall we have good predictions that are at least useful for pre-screening of type 3 choline chloride-based DESs. But COSMO RS is not just useful to predict phase diagrams. We can also predict solubilities using it. Solubilities are governed by the same thermodynamics that govern solid-liquid equilibrium. Solubility is solid-liquid equilibrium. And so we can use COSMO RS, for instance, to predict solubility of solutes in DESs, so ternary systems. And this is an example of a work we did where we used COSMO RS to pre-select DESs for the extraction of carnosic acid, carnosol, and other antioxidants from rosemary. So we generated the sigma surfaces of a bunch of HBAs, HBDs. We made a matrix, and we calculated the infinite dilution activity coefficients of these two solutes. And we were able to identify regions where supposedly we had good solubility. And then we chose a couple of these DESs as our solvents to experimentally test them. And you can even do this for higher order mixtures. You can add water to the DES. So this image is the same as before, but now with 30% of water added to the DES. So we're dealing here with quaternary mixtures, and COSMO RS performs well for those. And we can get that infinite dilution activity coefficients and use this as a pre-screening tool to choose the best DESs for a given target application. We can also use COSMO RS to predict vapor-liquid equilibrium. So we can use COSMO RS to predict the vapor pressures of DESs. I mean, the type 3 DESs, type 5 DESs, they have non-ionic species, so vapor pressures are small but non-negligible. And this is just an example for thiamethyl. This is the VLE at 0.5 atmospheres of this system. And the orange line is the prediction by COSMO RS, very, very accurate predictions, which is important not only for engineering purposes. We can think about processes where we evaporate part of the DES, but also from a sustainability point of view. We don't want them to be too volatile. Now, sigma profiles, they encode a lot of information about the polarity of molecules. And so we can infer interactions between components from sigma profiles, and any property, not just activity coefficients, that depends on these interactions can be modeled using sigma profiles. Of course, COSMO RS is a quantitative framework, thermodynamics framework for activity coefficients, but we can go beyond its scope by using machine learning approaches. And for instance, in this work, we developed QSPRs are in extremis machine learning, so bear with me. We developed correlations, QSPR correlations, to describe the solvatochromic parameters of DESs. And what we used as input were the HBA and HBD momentums of the sigma profile. So in essence, the integral of the HBD region and the integral of the HBA region. And we got very good results in describing the alpha beta, so acidity, basicity, and the pi of the DESs. These are the R-squareds, which of course allows us to then change the composition of the DES and explore the latent space of solvents with regards to their solvatochromic parameters. And you can see that DESs, this region here, allows us to obtain solvents that have very different polarities from common organic solvents. Even if you use blends, mixtures of organic solvents, you're usually limited to this region here, whereas when you use DESs, you can probe this region here. And finally, deep learning. This is a recent work where we used sigma profiles to train convolutional neural networks to predict material properties. And this is the architecture of those neural networks. These are deep neural networks, 2 dense layers, 2 convolution layers, and they work more or less like this. We generate the molecular structure of the compounds of interest. We then generate their sigma surfaces. We then generate their sigma profiles. We input these sigma profiles into a convolution layer, which then goes into a deep neural network. And from there, we predict material properties. And any property that depends on interaction energies, boiling temperature, aqueous solubility, vapor pressure, can be fitted, correlated, modeled, and predicted using this approach. These are just a couple of examples. These are the results for boiling temperature, for vapor pressure, and aqueous solubility. And this data set includes solids, liquids, and gases. You can see that by the range in the boiling temperature, the range in the vapor pressure, and the range in aqueous solubility. What's more is that these are deep neural networks, which are usually constrained to very big data sets. You need thousands of data points to train them. But because we're using sigma profiles and we're collapsing them using convolution layers, we are able to obtain these results for data sets with only a couple hundred of data points, which means that we can now use this approach to DESs. And now, why am I showing you results that are for organic molecules in general and not DESs? Well, it's not just shameless advertising, I promise you. It's that when we've been trying to expand this methodology for mixtures and we get very good results, but then when we try to expand it for DESs, we've noticed that there's a very big gap in the literature regarding DES mole ratios, regarding DES composition. You see, DESs are not defined by specific stoichiometrics, by specific mole ratios. For instance, this is methylthymol, and the shaded area is the composition window where this mixture is liquid at room temperature, which means that we do not need to constrain ourselves, for instance, to a 2-to-1 mole ratio or 1-to-1 mole ratio. We can change the relative composition of the DES, which changes its properties, namely its solvatochromic parameters, and also changes its target application, its performance on the target application, here exemplified by the extraction efficiency for 2 dyes and their selectivity. Now, this is very rarely done in the literature, and yet it's of paramount importance to train neural networks, because in other machine learning methodologies, because that's where they shine. We can use sigma profiles and composition as inputs to those machine learning methodologies and make all of these predictions, which would allow us to fine-tune DESs for target applications, but this data is missing. And so I would like to thank you for your attention, and also the research groups I've been working with, Professor Coutinho's group at Aveiro, Professor McGinn's group, and Professor Coulon's group at Notre Dame. A bunch of very smart, very nice people in this slide. Of course, thank you all for your attention.